Hey everyone, welcome back to the second section where we're going to talk about reflection and refraction. I just want to quickly go through in a little bit more detail about the diverging mirrors. So here is an example of a diverging mirror. So kind of goes back to what we had mentioned before. If you recall the previous question that we left off with, where we had a converging mirror that the lines ended up not actually converging and instead diverged, that we would have to backtrack the line rays. Pretty much the same thing is going to apply here. So here, when the rays come towards a diverging mirror, the lines will all diverge, of course. So the way we have to do it is pretty much the same concept as the converging mirror, where we're going to have to backtrack them, and it will turn out that all the lines will end up crossing through the focal point once again. Uh, the same lines are actually made when we do these. It ends up being a little bit trickier. So I'm going to quickly try to run through how you would do it. So here, I'm just going to make a random image. Doesn't matter where I really place it. And what we're going to do is we're still going to have, the first line, which is parallel to the principal axis, and then it's going to reflect, and it's going to reflect as if it was going through the focal point like that. So I'm just going to extend this out a little bit more, and I'll add in a little breaks so that you realize that this is the extrapolated line backwards. All right, that should be good enough. Um, there is another line that we would draw, which would be through the center curvature. So let me try to get this one angled properly, just like that. I'm gonna have to keep playing with this until I get the angle just right. There we go. So this is another one. Once again, I'm going to have to decrease some of these lines to show that these are the extrapolated lines. Um, One of the other lines that I'm going to have to draw would be the one for going through the focal point and then parallel. This one is actually going to be a little bit on the tougher side. Um, it actually is a little bit easier on paper when you actually have a ruler. So this one is going to go something like that'd be the focal point. Um, I'll have to actually erase this because this is not the line that I actually want to draw. So ignore this line. What's important is the line that ends up going parallel to the principal axis like this. There we go. And this is the extrapolated reflected line like that. I guess technically line also actually extends over here. So again, these three lines never cross. What ends up crossing instead are the three extrapolated reflections, and we end up getting this as the image created. Oh, wrong one. That. So a virtual image created on inside the mirror, and it ends up being smaller and upright compared to the original. So this is what you'd have to do. Again, it's a little bit tougher. A lot of times it's going to be a lot easier when you have a ruler on hand, because you could just place the ruler, figure out what the angle would have to be, and then again backtrack it right away. But the same rules end up applying. We have a line going through the center of curvature. We have a line that goes through the focal point and then parallel when it hits the mirror. Then we have a line that goes parallel and then through the focal point. All right. So just keep that in mind. They are a little bit trickier and they're going to look a lot messier, but you still want to know how lines are drawn in the diverging case, especially since while we may not focus too much right now on the diverging mirrors, when we talk about lenses, we're definitely going to talk about diverging lenses, and the same thing is going to apply with them. Um, so I wanted to say something else about the sign conventions, but it's not really going to play a part in right now. I'll mention it later on, but you definitely want to know. What I will say is just pay attention to the sign conventions just for what the image distance is. If it's on the same side as the real world is, then that's positive. If it's in the mirror world, it's the negative sign. All right. So here's our next question. So work on this. Again, draw a diagram. I know it doesn't say it, but might as well try it. And we'll go over to pause the video, work on this yourself, and we'll go over it in a second. All right. So here's a convex lens. So this is a diverging mirror. So what we're gonna do, I just want to do a quick drawing of this. So let me check real quick. 10 meters from the mirror with the radius of curvature of 16 meters. All right, so in my drawing, so this distance is going to be 16 meters. So 10 meters would be an image being formed right about here. Or sorry, the object is placed right about here. So again, my first drawing is going to be parallel line and then through the focal point. Pretty close on that one. There you go. I'm not going to erase them this time. I'm going to save some time there. We have through, oh, this one's going to be, oh, wait. Through the center of curvature. Try to get that a little bit closer. All right. And then the last line is going to go through the focal point. It's going to be like right about here, eyeballing it, and then parallel. All right. And they're all crossing right here. So my image is right there. So expect an image to be, I would say, 6 meters away inside the lens, small, probably like a third of the original height. All right. So we use this because of the fact that now the um, distance is inside the lens. Remember, I said that distances on this side are positive and distances on this side are negative because the actual focal length and radius of curvature are on this side. They're now negative. So even though I put circular the this radius the radius of curvature here and the focal length here, they don't actually exist there. They exist over here. So um, we're gonna have to make them negative. Plug these numbers in, and what we end up getting is negative 4.4 meters. So again, it's going to be inside of the mirror. I was close. I said -6. And then when we do the magnification, we get plus 0.44. So it's going to be a little bit less than half of it. Now, if you notice, because the mirrors in a lot of cars tend to be convex mirrors so that you get a lot of information in a small section. Um, they end up having those phrases, objects in mirror are closer than they appear. The reason being is because a lot of times the way our brains work, the smaller an object is, the further away it is. So again, even though we know from experience that The objects are just smaller because that's the way the mirror is. Um, it still doesn't change the fact that our brains will sometimes misjudge lengths and distances based off of the small image of the truck and the large image of the car that's also within that frame. So even though if you look at this, it almost looks like this truck is really fairly far away from the car, uh, in real life, it's probably, almost up to the back part of the car. It's probably one car length away, not even. All right. All right. So now we're going to talk about the other main thing of refraction. So I kind of mentioned this before, but the speed of light is about 3 times 10 to the eighth. This is the actual number for the speed of light, but you won't ever have to use that number. You can actually use the 3 times 10 to the eighth. Quick side note, the speed of light is actually a constant term. Now you might think, well, of course that's the basis of a lot of physics, but what I mean is more of the fact that in science we have certain measurements that are defined as something that makes it so that it is not changed, and then a lot of other units are going to be based off of those constant measurements. For example, time, which is defined in seconds. 1 second is defined as the amount of time it takes for a cesium atom to oscillate in its excited state a certain number of times. I can't remember, but it's defined as a real life physical phenomena that we can measure and pretty much compare things to. So that is a defined measurement. Now it turns out that length is not actually defined. Um, Length is a normally we would think that length is a fairly consistent measurement or a very basic thing that of course we would have it defined as something, but it actually isn't. It used to be defined as a certain length of an object, and then we would use that to measure rulers, or calibrate rulers to. But what they ended up doing was that they defined the speed of light as this number. And with that, with this definition and the definition for time, the length is used or calculated from this. So it's kind of like I forgot exactly what the wording of it is, but it's kind of like the length that light travels in a certain number of seconds. So that's like what distance is measured in. So it's kind of interesting that if it turns out that the speed of light is something different than this, or we do measurements that changes the speed of light, or makes our measurements for the speed of light more accurate, all it will do is just change what our definition for a meter is. It will not change the actual value of the speed of light. So, interesting thing for those who are just curious. All right, so as I said, in a vacuum, light travels its fastest, about 3 times 10 to the eighth. And then once it enters into new mediums, due to the particles now kind of resonating, if you will, or being interacting with the changing electric and magnetic fields, what it ends up doing is it causes light to actually move slower when it's in other things, typically like in water or glass or any other material. Now, the amount that the material will actually slow light down is based off of what's called the index of refraction of that material. So the index of refraction is a ratio of the speed of light versus the speed in that material. So for example, in a vacuum, the index of refraction is 1 because they are the same number. And in air, it is a very small difference. It does go a little bit slower in air, but it's very, very not noticeable. In fact, a lot of times when light's traveling in air, you can just pretty much assume that it's traveling at 3 times 10 to the eighth. But then when we get into water, we'll see that it ends up being slower than light by this amount, by 1.33. So the ratio being that light is 1.33 times faster in a vacuum than it is in water. Uh, and then in a material like diamond, it ends up being it has an index of refraction of 2.42. This is probably the highest that you will see, but we could have index of refractions even higher. One thing to note, that this is only for a specific wavelength of light. It actually turns out that the amount that light will, the index of refraction is wavelength dependent. And it's actually one of the reasons why we get things like dispersion, where light comes in and then gets that nice little rainbow dispersion effect because of the fact that different colors of light will actually reflect differently through a glass medium. Um, yeah, so I wrote that it's the absorption and re-emission of light, but that's not the only thing. Like that is somewhat happening, but it is also the atoms being affected and almost oscillating and interacting with the changing electric and magnetic fields. Now we do have an equation for this. It's called Snell's law. So Snell's law basically takes a look at this and sees how we can determine how an object interacts when it enters into this new medium. So when it's going straight in to a new medium, the speed just decreases. But if it comes in at an angle, then what ends up happening is that when it goes through that new medium, it's going to bend a little bit. Now, we did actually talk about this in the mechanical wave section. I made the comment about, if you're driving your car or you're pushing a cart, and you're you're coming in towards a new surface at an angle, one wheel hits that new surface and will end up changing its speed, either going faster or slower, which will cause the entire car to shift because one half of the car is uh, going at a different speed than another half. So that same thing happens with light, and that's what we call refraction. Now, the equation that we're going to use, what Snell's law is giving us, is n1 sine theta 1 equals n2 sine theta 2. Now, it's extremely, extremely important. This is what I mentioned before, that these angles are measured to the normal line. So the incident angle is from the ray to the normal, and the refracted angle is from the normal to the refracted ray. Uh, Now, one thing to note is that uh, one thing you'll see is that regardless of whether we're going from air into water or water into air, the light actually bends pretty much the same way. So, like here, when it's in the air, it ends up being a fairly big angle, and then it bends towards the normal. If we go the other way and we shine light here, which is already closer to the normal, when it comes out, it's actually going to end up bending away from it. So for the most part, the section that the wave is traveling faster in, that light travels faster in this case air, will always have the bigger angle. This is one way that you kind of make your life easy of a quick check is by reminding yourself that the faster that light is, the bigger the angle. So faster light, bigger angle. Slower light, lower angle. Another thing that also, the only thing that really changes though, is the reflected ray, because remember there is technically a reflected ray every time it interacts with the boundary. So the reflected ray would be in in this case still in the air, while here it would be within the in the water. All right, nothing too crazy. This is actually one of the things gives us, like I said, this optical illusion effect that you end up not realizing where things are um, in water because when you're looking at it from air, the location that it is in water ends up being somewhere different. So this is why it can be difficult to spearfish. Like you may see something in water and you may want to throw something at it, but you'll realize that you miss mainly because of the fact that it's at a slightly different location than where it actually is. So, for example, this straw, this straw might actually be more like over here, but it looks like it's over here. So you'll end up having to um, try to figure out where exactly it is based off of the refraction. So here you go. Um, the foot. So as I said before, our eyes see light as traveling in straight lines. So for example, because light uh, gets refracted, the foot that's over here will end up bending in a much bigger angle like here. But this person, as far as he's concerned, he sees the light as coming in a straight line and ends up being over here. So uh, it ends up being a really important thing to kind of keep an eye out for. And like I said, it's what kind of causes optical illusions for us. All right. So here's a quick question dealing with Snell's law. You could pause the video, work on this yourself, and we'll go over it in a second. All right. So here we have the light coming in. It goes from air into glass, and then later on it's going to go from glass back into air. And we want to know first, what is the angle of refraction as it enters into the glass, and then what is the angle of reflection when it reemerges. So in the first part, we're just going to do n1 sine theta 1 equals n2 sine theta 2. Figure out what the medium is here. You can kind of ignore my signs. You'll see why I'm doing that in a second. But what we end up getting is that when we plug the numbers in, the angle when it's inside the glass is going to be 35.3 degrees. So it starts off at 60. It's going to refract to 35, a little bit over 35 degrees. When it goes from glass into air, I kind of do the same thing, and I get that it's back to 60 degrees. Now, one interesting thing about this, because of the way that it's set up, it basically means that each segment, each section, follows Snell's law. So what I'm trying to get at is that if you have a material that goes, let's say, glass, air, diamond, liquid, it's got multiple sections, but you're only curious about one of the angles, you don't have to go through every single part. You only really have to go through one part that you know all the information for and set it equal to the one part that you're looking for the angle. So, for example, I could have done something similar to this by just going from air to air and then realizing, oh, because the indexes are the same, the angles are the same. So the only thing that happens as light goes through this glass, it doesn't actually affect the angle that it travels in here. All it does is affect where it's located. So instead of it coming in through over here, it's just put off on an angle a little bit based off of the thickness of the glass. All right. This is another question which you can work on real quick. We'll go over in a second. All right. So here, you're pretty much going to be using almost a small angle approximation, playing around with the trig functions. So this is when it's in air. Again, the angles are going to be really, really small, so we're just going to drop the sine theta part and just say that it's a theta, mainly so that we can replace this with x over y, or x over d, because theta is roughly equal to tan theta. And then from here, we could plug those numbers into our Snell's law equation. move some things around since the x values are the same, and we end up getting that this 1 meter deep pool actually only looks like it's 0.75 meters. So again, another thing that we had to kind of keep an eye out for with refraction is that it does make depths also hard for us to gauge. All right, so the wavelength range for the visible light spectrum pretty much ranges from 400 nanometers to about 800 nanometers, or 400 to 750. Ultraviolet is any wavelength that is smaller than this, and then infrared is any wavelength that is greater than this. Get it? Infrared, it's like lower red. Ultraviolet, higher violet. Um, so yeah, prisms are used to kind of show the effect of dispersion. Mainly the reason being is so that when the light enters into, as we said before, about how when light enters into a medium and then leaves, it's going to leave at the exact angle that it came in at, regardless of how it bent inside. And all that's going to do is just shift where it got bent from. So if you're looking through a flat piece of glass, you wouldn't normally see dispersion of the light kind of coming out as a rainbow, because all the light will end up kind of almost relapping with all the other rays of light. But with a prism, because of the shape of it being triangular, as the light comes in and causes all those lights to bend at all these different angles, when it hits the other side, which is bent at a completely different angle, then all the rays will end up bending differently when they come back out. And that's why we end up getting that rainbow effect with the prism, more because of the change in the geometry. And like I said, that rainbow color effect is what we call dispersion. So this is pretty much what's going on. You have white light coming in, it strikes the surface of the prism. The red light kind of barely gets refracted and kind of almost goes straight through, while violet light ends up bending the most and coming out like this. And then we end up, as it enters into the next surface, again, when it comes out, it's going to come out at completely different angles, which is why we get the rainbow effect rather than it coming in as white light and then leaving as white light again. Um, this is just an example of how the wavelengths change and how that affects a refractive index. So here you can see that red light over here kind of doesn't really the index of refraction doesn't really change too much until we get to the slightly higher um, wave or lower wavelength. Sorry, I keep thinking of frequencies. The higher frequency lights, like blue and violet, where it will start to refract a lot more. Uh, this is one of the reasons why our atmosphere causes the sun to look white, not white, yellow, and our sky to look blue, because the yellow light doesn't really refract and just kind of goes straight through, while the blue light does get refracted around. And also is why um, sunsets and sunrises end up having that, reddish effect to it. All right. Oh, so this is actually pretty interesting about where does it an actual rainbow get caused from? And rainbows do get caused by this similar thing, but it's actually a little bit more in depth than just dispersion, because it is also a part of reflection as well. So what ends up happening is that sunlight comes in, and then what ends up going on is when it hits the back of the surface, the light ends up, uh, reflecting backwards out of the water droplet on the other side. Um, and then same thing for the other water droplets. And the rays that do hit your eyes will cause you to see this rainbow effect. You know, red light being on top and violet light on the bottom. So a lot of times the way that you see rainbows mainly occur when the sun is behind you, or a lot of times sometimes will occur around the sun, not really in front of it. This also is where we can explain like double rainbows. Um, so with double rainbows, what ends up happening is instead of it being a occurring during the first reflection, the light will come in at such an angle where when after it reflects off onto the back to the front, uh, it won't be enough for it to transmit and will actually reflect again. So we get a what's called a second reflection. Um, Now, this second reflection actually ends up causing the colors to be inverted rather than be straight. So I just want to go back to the water droplet. So when the light comes in, it reflects off the surface here. When it comes to this surface, it reflects one more time before it comes out of the water droplets. And you end up getting, like I said, an inverted color scheme. So here you could see that the red is up top and the blue and violet are on the bottom. But if you look here, the red is on the bottom and the blue and violet are on top. Um, you'll also notice that the colors are a little bit dimmer than these, and that's mainly caused by the fact that there's not nearly as much light that's causing this one. There's also, because of the additional reflection, there's additional energy being absorbed by the water droplets, but it's also like not as much light is actually getting to this double reflection stage. Technically, you could have other higher levels of rainbows. You could have a triple rainbow, though I think that one would probably be really hard to see. Um, One interesting thing, I did have a video that I found online about it. If you want to see it, I can send it to you later. But basically, people skydiving and seeing rainbows, you can see the entire, circle of it. So rainbows actually come in circular shapes, not just arcs. So pretty interesting there. Now, going back, this kind of plays into a part about the double rainbow. Um, that if light enters into a medium or strikes the surface of a medium at a very extreme angle or a very special angle, the light actually won't transmit and will just end up reflecting as if it was a mirror. This angle is what we call the critical angle, where the light will come in and, based off of Snell's law, will end up having a refraction of 90 degrees. So any number that's greater than the critical angle will end up causing what we call total internal reflection, where all the light just reflects back into the medium and won't actually get refracted through. So here's just some diagrams. So you have a source in the water at this very steep, small angle. There will be some reflection, but also some refraction. As the angle increases, the reflection will also be there, and there would also be some refraction. But then once you get to this special critical angle, um, instead of refracting out, because the angle will always be bigger than the original, you'll have it come refract at a 90-degree angle here, and then anything greater than that will cause all the light to just be reflected. However, one thing to note is that this will only occur when N2 is smaller than N1, mainly because, as I said before, the faster light travels, the bigger the angle. So the faster light means smaller index of refraction. If it was the other way around, you can actually see it here, just reverse the direction of the arrows, that because water travels slower than air, its angle will always be smaller than this. So it would be impossible for this ray to have a not a less than 90-degree angle and create something in water that has something greater than 90. Uh, but for here, doing the reverse, it is always possible to find an angle that will not allow for refraction to occur when you go from slow to fast. So here, This is how you can find what the critical angle is. You basically use Snell's law and set the other angle equal to 90 degrees. So you can write it like this, but this is just using Snell's law. All right. This is kind of what total internal reflection looks like. Basically allows the light to actually curve along a path. So for example here, if you have water and it's traveling, normally the light ray would just kind of, it would go through the water, but it will eventually, move through it and like out of it. But because of the angle of this light ray and the water as it travels here, it will actually just continue to bounce off the surfaces as it goes through here. So these diagrams, like this is just kind of showing you how it kind of looks as it reflects back and forth. But it does allow you to send light through one area, and then this can curve almost freely, if you will, uh, and then allow light to exit in a completely different direction. And that's how a lot of fiber optics work. All right. You could try working on this problem. It kind of goes with the whole critical angle and total internal reflection. Try to visualize it as best you can. Pause the video, work on this yourself. You go over it in a second. All right. So here, first we want to figure out what the critical angle is. So when we use Snell's law, we get that the critical angle is 49 degrees. So what this ends up meaning is that if a person is sitting on the bottom of the floor and they're looking up, everything around them will end up like the entire surface of the water will actually be compressed into a circle that that makes an angle of like 49 degrees. So like the person's looking up and the angle between his eyes and the edges of the circle will end up making being 49 degrees. And then everything else outside of that, they'll be able to see the walls and surface of it. So it'll almost look like a what's the word that I'm looking for? Almost like a fishbowl or a like a dome or something like that. So this is an example here. Like the person will actually see everything that's above the surface being compressed into just a circle like that, and then everything around them will be reflected off of the water. There's actually a place in the world that does show this due to its size. Um, this lake in Austria. So, you know, feel free to check it out. All right. Now we're going to talk a little bit about refraction through cervical surfaces, but not really going to put too much focus on it. Not really necessary. Um, but this is kind of plays with what we're going to talk about later on with lenses and, of course, the human eye. So, for example, let's say we have light that's originating from some point as it comes out. When it strikes the surface, just like before, it is going to refract due to Snell's law, but because each angle, each line is going to come in at a different angle, that means they're all going to end up refracting at different angles. And it turns out that they'll end up crossing at once again at a convenient point. Now, if we want to figure out how these 2 points are related, we can, do some geometry with Snell's law. We have to play around with things. This, for those who don't know, phi is usually an angle from, here it's being used as an angle, an obtuse angle. So you have like theta 2, gamma, and phi because these three are all going to be equal to 180. Yeah, I'm not. We know that these two are going to have to be equal to 180. Or sorry, not those two. These two, beta and phi. Not really going to go into much detail with this. So if you want, you can look at this. But usually it's just playing along with geometry and stuff. We end up getting this equation for where the line will actually end up being located based off of things like where the object is placed, where the and then where the image is formed. This actually ends up leading to something called, well, actually, we'll talk about something called the lens maker equation, but that what we just did there kind of plays a part to it. Now, this works not just for convex lenses, but also concave lenses. And we end up needing to state some conventions. So right now, you don't need to worry about these conventions, but this is what's going to be a part when we start talking about lenses. So I'll go over this stuff later on. All right. So in summary, these are the equations that we've talked about. We talked about index of refraction. We talked about Snell's law. We talked about the mirror equation and the magnification of the mirror and all that stuff. We've also talked about, you know, things like drawing the ray diagrams. Definitely want to make sure that you know that in the future. All right. So these are the homework problems that are going to be due Wednesday. If you have any questions, please feel free to let me know. Otherwise, I'll see you later. Bye.